So we are expecting 12 people and there are already 10 attendees. So Wade, if you want to start, if Ugo is okay with that.
Okay. Whoops, I must go back. What should engineers know about ionizing radiation? Well, in fact, a lot of people are going to be discussing energy in the Gulf in the next few days. What I'm going to say is rather different. And it can be summarized by saying we have to prepare to repeal the Nuclear Red Flag Act. And I'm going to tell you what I mean by that. Everybody knows that today we need to worry about energy, and there are three basic sources of that energy. There's the pre-industrial sources of wind, solar, hydro, etc. They are weak, familiar, and very randomly reliable, in fact, unreliable. And then there are the fossil fuels, which have brought us to the civilization since the start of the Industrial Revolution. And they're very good and very acceptable. The problem is the pollutions and emissions that they cause and their effect on climate change. The stranger in this table is the nuclear column, the third column. And that has 1 million times the energy density, even of fossil fuels. And it has no emissions, small footprint, long plant life, and low waste. As a result of that, 1 kilogram of fuel, refined fuel, can provide all the energy for one person for the whole of their life, whereas it takes 1,000 tons of coal or oil or 10 million tons of water over a 100-meter high dam. There are big, big differences between these three columns. The first column will not support the life, standard of living that we expect today. The second is now seen to produce unacceptable pollutions and emissions. And the third one, the only problem is public fear, public safety fear. And this has caused very cautious regulations driving enormous cost. And it's that those red things that I want to talk about today. So these are the questions. Why is nuclear energy 1 million times more energetic than fossil fuels? You don't come across factors of 1 million every day. What keeps nuclear energy so safe? Why is nuclear radiation almost harmless to life? And what should the regulations now say on how should we engage the public? You won't get any of those answers, I think, in Abu Dhabi. A preliminary question is, where does the clockwork come for food and chemistry and electronics? Does it factor a 10,000 between the typical energy densities of biscuits, explosives, liquid natural gas, lithium battery, and hydrogen, much greater than the energy of hydro or solar or wind? Where is the energy stored? The answer to that question was, in fact, provided just 99 years ago by a rather small Frenchman, Louis de Broglie. shown there in this famous picture of all the great scientists of the early 20th century. And for his work, he got the 1929, he won the 1929 Nobel Prize for as alone. It wasn't divided with anybody else. It is what he did. In his PhD thesis, so all students should realize that things can be within their grasp. And what did he say? He said that all matter, all radiation, everything is described by waves. They are waves, but they're described by waves. And the wavelength is h, Planck's constant, divided by the momentum, which is h over mv, where m is the mass in kilograms and v is the speed in meters per second. And as we'll see in a minute, this is an explanation of chemical energy and nuclear energy in terms of can be translated into the kinetic energy half mv squared. Now, the secret is that these waves that he's talking about are like sound waves in a musical instrument, and the wave in a musical instrument is, of course, related to the size of the musical instrument, so that the wave is trapped inside the. So, if we look at atoms and nuclei, which in popular language are often confused with one another, but there's a factor of 100,000 times difference in size. And electrons are trapped in atoms, and protons and neutrons are trapped in nuclei with a factor of 100,000 difference in scale change. Let's do the actual calculation. It really is a very simple idea indeed. De Broglie said that the wavelength of the wave is h over mv, so that the size of the box, the musical instrument, if you like it, is half a wavelength, hence the little picture that I've drawn of a wave trapped in a box, and that tells you, since 2L is h over mv, you can calculate the kinetic energy, half mv squared, is h squared over 8ml squared. So all we need to know is the mass of what it is that is trapped, the electron, for instance, and L, the size of the box in which it is trapped. We put in the numbers. For an electron trapped in an atom, 10 to minus 10 meters, just put in the numbers and you'll get 7 times 10 to minus 19 joules, which is 4 electron volts. And per kilogram, if it's carbon, that's 35 megajoules per kilogram. This matches within a factor of 3 or 4 or 5 or even 10, all the energies of chemistry, batteries, laser, food, electronics, and so on. If we do exactly the same thing for a nucleus, we get L is 10 to the 5 times smaller, and the mass of protons and neutrons are 2,000 times larger, and that gives us 20 million electron volts. And this ratio, the ratio of ml squared, is 5 million. And this is the story of the 20th century, and 21st. Mankind has yet to accept the true benefit of this huge number. Now, So the second part of my talk is to look at the physics of the nuclei and how it provides safety, control, and stability. This is not a matter of technology. It's a matter of the fundamental physics. The first thing to note is that nuclear energy, nobody was even aware of it. And the only signs of nuclear energy that they could see, apart from the sun, which was sort of taken as given, was the inside of the Earth was too hot. It was calculated that it should take a few million years for the Earth to cool down, and yet it seemed to still be hot inside after 1,000 times longer than that, since it was formed. And Lord Rayleigh, in the end of the 19th century, published a paper in which he said there was a problem here. And the other sign of nuclear energy was what arrived from otherwise careful Frenchmen who left some crystals on a photographic plate for a few days in a dark drawer, and then found some unexpected results. And that was the discovery of nuclear energy. So it is, in fact, so well controlled that it doesn't happen most of the time. Let's look at why it doesn't happen. Well, collisions between nuclei are prevented by the huge electrical barrier. They're very highly charged and very small, so they can't reach one another. So there's just no fraternizing between nuclei on Earth. Just doesn't happen. What can happen is nuclear breakup, or otherwise known as fission, activated by neutrons. Now, neutrons are neutral particles, and so they can overcome the electrical barrier, but it's made safe, or it is safe, because neutrons are, first of all, they're easily absorbed by other nuclei, and the other thing is that they only have a lifetime, about 10 minutes. So it's as if you invent a lock, which is absolutely foolproof because the key self-destructs every 10 minutes. It is extraordinary protection of nuclear energy. So that's why fission is safe, and it was only with great difficulty that a way was found with neutrons to extract nuclear energy. And then there's radioactive decay of unstable nuclei. Well, unstable nuclei, because they're unstable, they don't need to interact with another nucleus to release their energy. And this is uncontrolled and emits ionizing radiation of the kind that is found in the Earth and keeps the Earth hot. And the radiation that is emitted by radioactive decay, which is what people worry about, only damages atoms and molecules. It doesn't damage nuclei. It doesn't have enough energy, at least not except in an intense research lab. So radiation only damages atoms and molecules and life and so on. So that's serious, but it doesn't touch nuclei. And the result of this is that radioactivity and its radiation are not contagious. Radiation doesn't make people or anything else radioactive. Now, there are a lot of very sad stories, both after Hiroshima and Nagasaki and after each of the various accidents, that people thought that because somebody had been affected by radiation, they could pass it on in some way, that it was infectious. But it isn't. Fire is infectious and spreads. Viruses are infectious by definition and spread, but radioactivity and its radiation are not contagious. But nobody ever says this, even to people who were involved in looking after people after an accident. So what does radiation do to living tissue? Well, there are several stages. The first thing happens within seconds. An exposure to radiation damages a limited number of cells. We'll explain why limited number in a minute. The live tissue then reacts to recover from this damage in a period of hours and days. That's what live tissue, dead tissue doesn't do anything like that, but live tissue does recover from radiation. How and why we'll explain in a minute. How does it do this? Well, it energizes oxidants. It quenches energized oxidants. So it mops up activated, overexcited atoms and molecules. It repairs DNA. It replaces cells by writing them off and putting more in their place, and so on. And when the cells restock these resources after an exposure, replacing the antioxidants and the enzymes, it, to be on the safe side, adapts the reaction by adding further stocks of antioxidants and enzymes. And this means that it has the benefit of adaptive feedback. And this increases the threshold for failure. Look at the next slide. So on the left, you've got a typical feedback from a stabilized of a stabilized system, whereby up to a certain stress, the response is quenched. It doesn't happen, and only at a certain point, you get threshold of failure. If you have adaptive response, then as a result of this experience, the resources are increased, which has, of course, a cost, a resource cost for the biology. And the net result is that the stress, the threshold is raised. And if it happens again, an exposure happens again, the response will not fail except at a higher threshold. Well, a good example of that people are familiar with and aren't frightened about, but is actually much more serious, is ultraviolet radiation and sunburn, and indeed skin cancer. Now, when people from northern climes go for a nice holiday in the sun, for the first few days, they limit their exposure in the sun, and they tell the children not to go out in the sun at the height of the day, because their skin is acclimatizing them to the effect of ultraviolet. Now, ultraviolet is like X-rays, only a slightly longer wavelength, and it ionizes the skin molecules and cells just like X-rays do, although the numbers are slightly different. Now, after a few days, when the skin is acclimatized and has had this adaptive feedback, it's capable of standing more radiation, and after a few days, you can go out in the sun. If you overdo it and you go over the threshold, then some cells die and the skin peels away. And as we know, in a period of a week or so, the skin recovers. And only when only after a long time may the lack of response may there be skin cancer. But it actually is, there are more cases of UV skin cancer than ever there are from nuclear radiation and X-rays. Now, we've got to look at some numbers. The power, let's look at the power absorbed ionizing radiation is tiny and it's local. 1 gray or 1 sievert, as it is called, is defined as 1 joule of absorbed radiation per kilogram of tissue. And if you put the numbers in, then a safe radiation exposure, which, as we will see, is something like half a gray per year. And that represents 60 nanowatts per kilogram of deposited energy. Now, interestingly enough, normal metabolism, that is to say, the normal rate of energy production in living tissue, is about one watt per kilogram. So 60 nanowatts per kilogram, you can never feel. So nobody can feel ionizing radiation, but they can feel ultrasound or an MRI scan, or they could do, and that is held at about 1 watt per kilogram. And so the safety of ionizing radiation has to be kept much, much lower. The question is why? What is different? Well, this is a quantum effect. Ionizing radiation is absorbed not thermally. It doesn't work by making the tissue and the molecules hot. It works by damaging a tiny number of collisions very hard, and most of the molecules are not hurt. This, in fact, is really what Einstein discovered in 1905. He did 3 things in 1905, any one of which could have gotten a Nobel Prize, including relativity. But he actually got the Nobel Prize for his description of the photoelectric effect, which was the application of quantum mechanics to the ionizing process. So the effect of this is that life has to cope with a small number of severely damaged sites, and the rest are untouched. And what has happened is that over 3 billion years, life has evolved to isolate, repair, and replace those few damaged cell sites. And if it hadn't learned to do that, we shouldn't be here. Now, as far as animals are concerned, that's the end of the story, except for extreme doses, which we'll discuss later. But for humans, unfortunately, humans have discovered instruments to detect radiation at moderate levels and scare the pants off them for one another. So life would be much safer and happier if they didn't have these instruments. But we have to talk about what is a moderate level and what happens when that breaks down. In the early 20th century, one of the most famous cases of radiation-induced cancer was what happened with the dial painters. These were mostly young women who painted the faces of instruments, particularly in the First and Second World War, with radioactive paint, which then, because it's got its own internal energy source, would glow in the dark and could be seen in air instruments and so on could be seen when the lights go out. Now, radium in the paint is like calcium, and it is absorbed into the bones. It's got a very long half-life, and so effectively they get it goes into their bones and it remains radioactive essentially the whole of their lives. But in order to make a good job of this painting, the girls learnt, unfortunately, to lick the ends of their paintbrushes to get a fine point on the brush. And so some of them got bone cancer, and their bones remained radioactive all the way. Now, bone cancer is in fact quite an unusual form of cancer, and it only affects about 1 in 400. So I'll show the data in a minute, but out of 1,339 painters who had less than 10 gray, there were no cases of bone cancer, although you would expect about 3 by chance. That's 1 in 400. 191 painters had more than 10 gray, and there were 46 cases of bone cancer, and you expect less than 1 by chance. On the left is a plot of the absorbed, measured, this is data now, absorbed radiation dose in their bones throughout life. And on the x-axis is the year that they entered into this dial painting industry. And you can see that this is the full 1,339 cases. And in 1926, shown by the vertical line, was the first seriously successful case of radiation protection, when the girls were told to stop licking their paintbrushes, and the effect was dramatic. Now, on the plot on the right, it shows the data for those who did get bone cancer. And first of all, you see that they're all before 1926, although there's more plot to the right, but there's nothing in it. And everyone, all of those who got bone cancer had more than 3.7 millibecquerels of radiation in their bones. And all the data points are in that top left-hand square. And this is 1926, so there's a long, long, long before Hiroshima and Nagasaki and that sort of thing. So there's a clear threshold of 3.7 millibecquerels. It's a funny number because it was expressed in terms of an old-fashioned unit called curies, but the threshold is there. As a result of all this, the radiation people, protection people of the day, who conferred internationally in 1934, they agreed safety regulations which said what this threshold should be. And it was in their units, see the bottom arrow pointing at, in their units was 0.2 international roentgens per day. Well, that in modern speak is 2 milligray per day. And amongst those, the members of that international committee was Lauriston Taylor, who 46 years later, in 1980, said, "We know all we need to know." In 1980, we know all we need to know, and nobody has been hurt since at that level, and that remains true in 2023 as well. They got that level of radiation protection right, and it's what happened since then. We messed up the politics and the sociology of radiation protection, but they got the numbers right. There was, of course, something else going on, which was the use of radiation for personal health. And Mary Curie, who died in 1934, in fact, she did die of cancer, but lots of people die of cancer, but not, she lived to the full life expectation of a woman of her age. And of course, she got Nobel Prizes in physics and in chemistry, but her gift to the world in particular was in medicine for the diagnosis and for and cancer and therapy of cancer. And one of her often repeated mottos was, "Nothing in life is to be feared; it's only to be understood." And oh my goodness, if only more people would follow her. So in 1934, they'd got the right answer. What happened after that? Well, in 1945, nuclear energy, with this factor of 1 million, was used for war. And that's when things went pear-shaped. The 1950s, in particular, was an era of worldwide fear and distrust after the success of the Second World War, the failure of the Korean War, the distrust of the Soviet Union, and so on, and the Trump-like urgings of Senator Joseph McCarthy in the United States. The world, or rather the USA, demonized nuclear energy. One of the ways they wanted to do this was to stop the nuclear arms race, but that was different from whether radiation and nuclear energy itself was safe. And one of the things they did was to exaggerate the caution of the 1934 regulations by about 1,000 times, without any scientific evidence to do so. And that is what is called the LNT model today, of which more later. Why have we allowed this to happen and persist for 70 years? This is ghastly. High radiation doses are welcome for personal health. It's a good idea to draw a picture with color, a colored picture, to persuade people. We can show things as daily doses, as areas. Now, if you have cancer therapy for cancer, then every day you will get a dose equivalent to the area of the red circle every day to kill cancers in a cells in a tumor. And most people who do that, who receive that, go away and say thank you for it. The tissue around the tumor may well get like 2 gray a day. That's the yellow circle. And usually that survives, the cells recover, and that ends happily. If not, the oncologists are watching for it and can do something about it. The green circle represents 2 milligray a day, so that's 1,000 times smaller, and that corresponds to the agreed safety level of 1934. You can see how much smaller that is. There's a huge level of safety built in there for 1934. But unfortunately today, the official public recommendations since the 1950s are represented by that little white dot you can probably hardly see, which is 1 milligray a year, which is, as I say, it's out by a factor of 1,000 compared with the evidence. We need some more data. Animals, of course, are blissfully unaware of all this, and so they are a good, unbiased source of evidence. So the animals in the radioactive region around the Chernobyl reactor are blissfully unaware. They're still radioactive, but they're thriving. They haven't been shown any shock horror documentaries on radiation. Evidently, nuclear radiation is harmless at the low and moderate doses that they have received. But animals can also be used in the laboratory, less kindly. For instance, you can do it with mice, but mice don't live very long anyway. Better evidence comes with from dogs, and to have this is to show some data for 2 lots of dogs. One lot are which are treated in exactly the same way throughout life, and one lot are given 3 milligray, that is 1.5 times the 1934 figure, every day throughout life, and the other group was given no dose. And for the first 3,000 days, that is 8 years, until they're 8, there's really no difference between the 2 mortality curves. And none of them die, either who are irradiated or not. But after 8 years, that is to say, after 9 gray of radiation, which is about what the dial painters got, there starts to be a difference of about 10% in the mortality, and those who have been irradiated suffer more than those who haven't. But still, notably, that you can see the data points here are coded by whether they died of a fatal tumor or other causes. And it's apparent that those who had no dose have suffered from fatal tumors somewhat less, but not that much less than those who were irradiated. So that shows that, or suggests that, the kind of figures that were got from the dial painters from 1934, from experiments on animals today, are all in the same region. Not exactly 10, 20%, factor 2, 3 here and there, but similar. And it's a factor of tens and thousands that we've got wrong. Now, it's important in life to speak out when something is not right. There's in the UK now, if you go on the railway, there's an announcement which says, if you don't see something that looks, if you see something that doesn't look right, speak to staff and we'll sort it out. See it, say it, sorted. And this is fine, except when the staff, when the authorities are wrong. And famously, Hans Christian Andersen, in his story of the Emperor's New Clothes, when the what is going wrong goes all the way up to the king, the emperor, then of course it looks silly, and a small boy can shout out that you've got it all wrong. Well, we've got radiation all wrong for 70 years. And what are we going to do about it? Well, famously now, this is a letter dated June the 5th, 2023, which was written by the president of the Health Physics Society. This is the society of 2,500 professional experts in radiation safety. And he wrote to Congress this letter saying that, there he is, and he said, in a rather sort of pompous way, request for an oversight investigation to ensure that the latest science is incorporated into the radiation protection for low-dose environments. Well, actually, what that says is that the present thing is rubbish, and we cannot afford this sort of nonsense to go on when we need the energy of radiation. And he was supported in writing this letter by 7 of his predecessors, who will also appear at the bottom of the letter. And he is also now, the society then consulted its entire membership, and the letter was supported by the membership of the Health Physics Society as a whole. So let's look at the big thing. What did radiation do at Hiroshima and Nagasaki? Now, about 100,000 died from the blast and fire, and the health of the survivors and their children have been followed for 50 years and more. First of all, there is no evidence for inherited abnormality, which was the main source of public concern in the 1950s and 60s. So people don't get 3 eyes and 4 arms as a result of radiation. That is just for science fiction. Many survivors, of course, died of cancer and leukemia in the period of 50 years, from 1950 to 2000. And by comparing those numbers with the residents who were not irradiated and lived somewhere else, it has been shown that those who received more than 0.5 gray had a higher risk of cancer or leukemia. But the numbers weren't very high, although statistics are quite good, because you're talking about nearly 100,000 people. But the total excess cancer mortality, not per year, but over 50 years was 500, comes out 573. That's less than a third the number of those who died from the inept evacuation at Fukushima. So the conclusion is that blast and fire, fear and panic are the killers, not radiation. Well, this is my last slide. I don't know how he wasn't very good at school, but he certainly got his act together by 1931. Winston Churchill wrote in the Strand magazine in 1931, the coal a man can get in a day can do 500 times as much work as he can. Nuclear energy can do 1 million times more. The discovery and control of such sources of power would cause changes in human affairs incomparably greater than those produced by the steam engine 4 generations ago. That means the Industrial Revolution. He was right. Now we know that nuclear energy is far safer than feared. And we can tell everyone there is no need for the red flag that people used to wave in front of cars before 1896 because of the danger, the public fear of having locomotives, steam engines on the highway. The regulations that obstruct and delay the regulations that obstruct, delay, and overprice the energy source we need have got to be changed. That's a duty for all of us. Thank you.
Thank you very much for that, Wade. Sorry that I was a bit late earlier to people with a bit of technical issues. If anyone has any questions to him, please raise your hand in the audience. And I can allow you to talk, or you can read it out directly. I've just got a question for you. In the nuclear industry, as somebody that's now work there, the first thing they would tell you is safety, right? It's sort of the grand plan. And we are here telling people to review the stuff in the light of the new evidence coming out. When you speak to professionals, I mean, our physics society's got lots of members. What is the response that you get from the industry? Are they receptive, or are they blocking this line of inquiry?
Well, that's why, having written this letter, there was then a poll of the 2,500 professional members of the Health Physics Society saying, do you back this need for a complete reconsideration of nuclear safety? And as I say, there was overwhelming support for the investigation. Now, there isn't research to be done. It's not. They got the right answer in 1934, but we've got a lot of public policy and education and explaining of the kind that I'm trying to do now, and with Hugo's help and so on. There's a lot to do, but don't think that we've got a lot of research. A lot of is discovered in biology every year, and there are more Nobel prizes of people who've learned how it works. But the upshot of it is that it is safe.
That's great. Rajiv, your question?
Yeah, hi, Reid. Thank you for this insightful talk. My question is, I was in UK a month back for a nuclear institute organized young generation professional networking event, and I had some speakers who were absolutely having no connection with nuclear, but they were very eager to understand the way nuclear technology works. My question is, what role do you think industry has to play in sensitizing the common man about these fears which are set into their minds?
Well, of course, one of the problems in these things is that politicians are in the business with a 5-year time scale of basically telling people what they want to hear so that they get elected 5 years later. Our problem of getting the change of culture is going to take two generations. It's going to take 30, 40 years. So politicians don't help much. And if they were scientific, they wouldn't have gone into politics. So they don't know, they don't have any knowledge themselves of the background. Industry has got shareholders, and they're not looking just at 5 years. They're probably going to look at 6 months. The short-term reactions of almost all players in this business is not matched to the problem. Of course, you would expect the pensions industry, at least, to take a long view, and that's at the level that people should start. Then there's the industry like the shipping industry. Now, the shipping industry is rather responsive because a ship lasts for, has a lifetime of like 20 years. And the shipping industry is seriously interested in nuclear power, especially as the kind of small modular reactors that are being designed now would match the requirements of a significant sized ocean-going ship rather well. So that's a very positive development. And the shipping industry does not have to respond to local NIMBY, I think, quite so much. So through the International Maritime Organization, industry can get together and decide. So this is the kind of thing that is happening faster than the local political worries. But of course, people who do have access to have experience of nuclear power because they've got a nuclear power station around the corner already are usually the people who, partly because it provides them with jobs, but also because it hasn't caused them any trouble, and they just see it as a source of stability, and it's part of their life. So local political involvement with building nuclear power plants. It's no good having a nuclear power plant which is 300 miles away and expecting people to love it. They're only going to love it if it's just around the corner from them, or 30 miles away from them. If they've got an uncle who works there, their children go on a school visits to see the nuclear power plant, then the thing will become incorporated into people's reactions that, yes, they will vote for nuclear. Distant things they can be dismissed.
Right, there's a question from the chat I'll read out to you. Is if you're aware of any politician that openly supports reducing or reviewing the current nuclear regulations. Maybe you can tell about your experience in South Korea.
Well, I was invited at their expense to spend a week in South Korea, and that was their concern. They know how to build nuclear power stations. They have exported them to UAE and so on, but their concern was the public perception of it. So they are concerned with just the kind of problem. And so when I was there, I gave several lectures to all sorts of people and press conferences. And it was just at the point where the Japanese were about to release the cooling water from the Fukushima reactors. And I said, not only just that I would happily drink that water, but here's why I would drink it, because the numbers show that it would be no more dangerous to me than the radioactivity that is in my blood already. And they were very interested in that, and I was invited by the politicians to have a session in their parliament with a group of their politicians, with the press and everybody there, and that was, so I had 2 hours, nearly 2 hours of that with translation and so on. Now I have to say that I've never got that kind of reaction in the UK.
Yeah.
I wish I could.
Another question for you. What do you make then of the exclusion zones at Fukushima and Chernobyl and these areas? Is it worth repopulating them? Is it worth looking at?
Well, I don't think the animals would think so. I think the animals have a wonderful wildlife park, and I think having established a wildlife park, I showed a picture of a cheetah there. No, or was it a lynx? My zoology is not that precise. I think they should be preserved as memorials to our folly, and for the benefit of the animals.
All right, that's a very good answer. If anyone else got a question, raise your hand. Otherwise, I think it's already at 2 o'clock of the hour. Okay, I don't think we've got any more other questions. Thank you very much, Wade, for the opportunity. I forgot to do the introduction earlier, so just for record, he taught hell physics at Oxford, so it's not somebody who doesn't know what he's talking about. I hope I missed the first introduction, so I don't know if you introduced yourself.
Well, no, I did. I didn't, but
okay.
There's just one other thing I wanted to say. One of the problems is that as all societies, we separate different disciplines, so that people who know about nuclear don't know about biology, and people who know about biology don't know about nuclear, and people who know about politics don't know about either. So we don't have the personal trust in when these things are connected to one another, which is what we're talking about here. We don't have people who are prepared to take responsibility for the boundaries between these subjects. And so our education system is at fault. With AI, perhaps we can say, right, we're going to spend more time not only looking after old people like me, but anyway, I'm all right, and young children, but also spend more time educating and continually educating and keeping our education up to date. But we're talking about 1931 and 1934. That is stuff that's been around for a long time. So people should know, but unfortunately, they've been so frightened by the sort of nuclear ghoul and too many horrifying videos. And of course, the people who make videos and the press are very happy to misuse this for entertainment purposes. But watching or rather reading murder thrillers doesn't mean to say that you're encouraging murder.
Right. Well, Wade, on behalf of the French chapter of the Institute of Civil Engineers, I'd like to thank you very much for the presentation, and thank you everyone for attending.
Well, I'm very happy to talk with anybody. Wade.Allison at physics.ox.ac.uk. Communicate with me. 2 books which I showed on the. This is what I do.
All right. Thank you very much, and thanks everyone.